Okay, this is section 4.3, rational functions. We have just two definitions here. A rational function is a function that can be written as the ratio of two polynomials, p of x and q of x, each of which can have their own degrees. Okay, so notice the degree of polynomial p is right there. It's p, and the degree of polynomial q is q. Okay. Now, in order to be able to graph rational functions, we need these things called asymptotes. Kind of a funny name, but they're very useful for graphing. A vertical asymptote of a rational function is a vertical line x equals a, which marks where the y values of a rational function tend towards either positive or negative infinity as the x values approach a. Vertical asymptotes occur at x values which make the denominator 0. So vertical asymptotes correspond with the zeros of the denominator polynomial. A vertical asymptote will always coincide with a point that is restricted from the domain of a rational function. So yeah, you should think of a vertical asymptote as just denoting a point that's not in the function, right? Because we're that point gives us division by 0, so it has to be restricted from the domain of the rational function. Okay, so here's an example of a rational function, f of x equals 1 over x minus a. And then these graphs below here demonstrate what can happen at a vertical asymptote. So the red line, the blue dashed line is the vertical asymptote, and the red line is the maybe part of the curve of the graph of the rational function. Not necessarily this particular rational function, but and notice we use this notation. We say, like for this first graph, we would say that y is going to infinity as x is going to a from the positive side. So really this right here, it's fuzzy, but it says a with a superscript. So it's this. It's a with a positive sign up in the superscript. Okay? And what that means is, so y goes to infinity as x approaches a from the positive side of a. In other words, from the right-hand side. So we're talking about this graph on the right-hand side of the asymptote there. Okay? Now notice over here we have, this is a with a superscript minus sign. Here we have y approaches infinity as x approaches a superscript minus, which means as x approaches a from the left-hand side, from the negative side of the number line. Okay? So notice our x values are getting closer and closer to a, but from the negative side. This goes off to negative infinity, doesn't it? Okay, and then similarly here we have, in this third graph, we have as y goes to negative infinity as x goes to a from the positive side. And finally, the last one, we have y going to negative infinity as x goes to a from the negative side. Okay. Third definition here. The horizontal asymptote of a rational function is a horizontal line y equals b, which the graph approaches as x goes to plus or minus infinity. The horizontal asymptote of a function can be determined by comparing the degrees p and q of the numerator and denominator polynomials. So notice, and notice this is singular. A rational function will always, if it has a horizontal asymptote, it'll always just have one, whereas rational functions can have multiple vertical asymptotes. Okay, now how do we determine the horizontal asymptote of a rational function? Well, there's three cases. We could have, there's three types of ways to classify. There's this one simple way to classify rational functions, and that is by the degree of both the numerator and denominator polynomials. And so you might, I call the kind where p is less than q, in other words, the numerator degree is less than the denominator degree, I call that a bottom-heavy rational function. Okay, and then in that case, your horizontal asymptote will just be the line y equals 0. We could have p equal to q. This is the neutral case. And to get the horizontal asymptote, then we use, so when p equals q, we use this formula, y is equal to a sub p over b sub q. What is a sub p and b sub q? It comes from this generic way of writing a rational function up above. A sub p is the lead coefficient of the numerator polynomial, and b sub q is the lead coefficient of the denominator polynomial. Okay, so if we take if p is equal to q, then the horizontal asymptote will be a sub p over b sub q, just the line y equals that ratio. Okay. Finally, the last case is if p is greater than q, if the degree of the numerator polynomial is greater than the degree of the denominator polynomial. In this case, we don't get a horizontal asymptote at all. In this case, we get what's called a slant asymptote. Okay, and we will actually see a case of that today in this lesson, but so it does have an asymptote, but it's going to be either a slant asymptote, or it could be even higher degree, like it could be quadratic, and then it would be like a parabolic asymptote, but then it's kind of weird to call it an asymptote then because it's not a straight line. Okay. The key idea about asymptotes, though, is that they are lines that the graph of the rational function gets closer to. Okay, so with vertical asymptotes, as your x values get closer and closer to the x value of the asymptote, then the function will either blow up to positive infinity or negative infinity. Okay, whereas horizontal asymptotes, these give us the long-run behavior of the rational function. Okay, so vertical asymptotes are part of the short-run behavior. Horizontal asymptotes give us the long-run behavior as x approaches positive or negative infinity. So this is the limiting value of the function as x gets very large in magnitude. That's what a horizontal asymptote gives us. All right. So we have a rational function here given f of x equals 3x minus 8 over x plus 7. Find the following. The domain in interval notation. So here we have, we can't allow x to be, so x is not equal to negative 7, right? If x is equal to negative 7, we'll get division by 0. So the domain in interval notation would be all real numbers except negative 7. How do we denote that? Well, we want to go from negative infinity to negative 7. And then from negative 7 to positive infinity. And we don't want to include negative 7, so I've used rounded interval symbols there. There we go. There's our domain. The y-intercept is at the point. How do we get the y-intercept? Well, you just evaluate the function at 0. So what is f of 0? F of 0 is going to equal, let's see, in the numerator we're just going to get negative 8. In the denominator we're going to have 7. So the point would be 0 comma negative 8 sevenths. Okay. The x-intercepts are the points that make the numerator 0, right? So what x value will make this 0? So 3x minus 8 equals 0, or 3x equals 8, or x equals 8 thirds. And so we get the point 8 thirds comma 0 for our x-intercept. Okay, now vertical asymptotes, these correspond to the values which make the denominator polynomial 0. And in this case, it's at x equals -7. And finally, the horizontal asymptote is at, well, let's see, which case do we have here? So this is the case where the degree of the numerator is 1, and also the degree of the denominator is 1. They're equal. So we take the ratio, our horizontal asymptote will be the ratio of, remember it's this a sub p over b sub q, where a sub p is the coefficient of the numerator polynomial, of the leading term of the numerator polynomial, which would be 3 in this case, and b sub q is the leading coefficient of the denominator polynomial, which is 1. So we get 3. So it's just the line y equals 3, a horizontal line, y equals 3. Okay, so when graphing rational functions, we're going to need to go through all of these steps, basically, except perhaps finding the domain. That's the same as finding the vertical asymptotes, right? So we'll need to go through steps B, C, D, and E in order to graph rational functions, okay? Let's practice a little bit more, though, before we start graphing with another rational function. Here's f of x. F of x is equal to x, quantity x minus 4 times quantity x plus 2 over quantity x minus 9. Okay, the domain. Again, x here, we just can't have division by 0, and if x equals 9, we're going to get division by 0, so x is not allowed to equal 9. And in interval notation, that would be the interval from -infinity up to, but not including 9, unioned with the interval from 9 to infinity. Okay, the y-intercept, well, we just evaluate the function at 0. F of 0 is going to give us, let's see, -4 times +2, just setting x equal to 0 in the function definition, and we divide by -9. So that's -8 divided by -9, that's 8/9. And so the point is going to be, all points on the y-axis have an x value of 0, and then the y value will be 8/9. Okay, the x-intercepts. Well, the values that make the numerator, this polynomial is nice, it's already factored for us. So the values which make the numerator polynomial correspond to the x-intercepts. And this is simply because whenever you have a rational function, your question is, well, where are the outputs of this function equal to 0? Well, a ratio is equal to 0 when the numerator is 0. 0 over 1 is 0. 0 over 2 is 0. 0 over 3 is 0 over anything is 0, with the exception of 0 over 0, which is just undefined, right? But the vertical asymptotes take care of that. So the point is, to find the x-intercepts of a rational function, you just need to find the zeros of the polynomial. The numerator polynomial. And in this case, it's 4 and -2. So the points on the graph would be, well, in order would be negative 2 comma 0 and the 0.4 comma 0. The vertical asymptote, there's just one in this case. It's at x equals 9. The horizontal asymptote. So let's see, we have to compare the degree of the numerator polynomial with the degree of the denominator. The numerator is degree 2, the denominator is degree 1. So this is the top-heavy case. The top-heavy rational function does not have a horizontal asymptote. It'll have a slant asymptote in this case. So we just say none. No horizontal asymptote. Okay. Sketch the graph of the rational function. Okay, so what do we need to do? We want to find the x-intercepts, the y-intercept, the vertical asymptotes, and the horizontal asymptote. And then we will also use the multiplicities of every zero. Those multiplicities will guide us when graphing as well. Okay, so let's see here. Let's see. Let's start with, I guess, x-intercepts. The x-intercept here, well, when 2x plus 1 equals 0, right? 2x plus 1 equals 0. That gives us x is equal to negative 1/2. Okay. What about the y-intercept? Well, we just evaluate the function at 0 to get the y-intercept, and we get 1 over negative 3. Which is, of course, negative 1/3. Okay. Next, vertical asymptotes. We only have one here because there's only one value that will make the denominator polynomial 0, and that is x equals 3. So I'll just denote this with v-asy. We get a vertical asymptote at x equals 3. Finally, the horizontal asymptote. If there is one, there will just be one. And how do we get it? We compare the degrees of the numerator and denominator polynomials. They're the same. They're both degree 1. So we take the ratio of the leading coefficients, which are 2 and 1. So our y-asymptote is just going to be y equals 2 over 1, which is 2. Okay. So now we want to plot these points and lines. Okay. So first, I'm going to plot the x-intercept. That's at x equals negative 1/2. That would be right here. The y-intercept is at negative 1/3, which would be about, here. We get a vertical asymptote at x equals 3. So oops. Okay. I like to do my asymptotes with maybe like a dashed red line. There we go. And a horizontal asymptote at y equals 2. I'll do this in a red dashed line too. Although sometimes I use green, but you can use whatever colors you like. Okay. Okay, so now we have everything plotted that we can glean from the function. We have our all the x-intercepts, there was just one, the y-intercept, and all of the asymptotes. Now, one of the key ideas is that as x gets very large in the negative direction, the graph is going to have to get closer and closer to this line, y equals 2. So it's going to do something like either like this or like this, okay? But it can't be this case because there's these 2 points down below that my graph must cross through, okay? So let me delete all that. So I've got to go through these points, and the other thing is the multiplicity of the 0 in the numerator was just 1. So I'm going to be crossing the x-axis. So just like with polynomials, okay, just like with polynomials, the multiplicity tells us whether or not the graph will touch the x-axis at that 0 or cross. Odd multiplicity tells us the graph will cross at that 0. Even multiplicity, the graph will touch the x-axis at that 0. Okay, and we've also got to go through the y-intercept here, so. And then as my x values get closer and closer to 3 from the left, the graph has to get closer and closer to that vertical asymptote. So my graph could either do something like this, or it could maybe turn around and go up like that. But it can't go up like that because it would have to cross the x-axis, and there's no zeros in that region. So I can safely eliminate that possibility. Okay, so we know it's going to do this scenario here. And then, of course, as x gets large in magnitude in the negative direction, I've got to get closer and closer to that horizontal asymptote. So what am I going to do? I'm going to connect these 2 lines, here, and do something like that. Okay. Now, there are no zeros to the right of x equals 3. So my graph definitely can't do something like that. It can't cross the x-axis to the left of x equals 3. So it means it has to be up above here. It has to do something like this. Whoops. Okay. And we could plot some points. There's no shame in computing, throwing some x values into your function and plotting points if you're unsure of yourself, okay? Don't feel ashamed doing that. That's perfectly fine and a good thing to do when graphing a rational function. One other thing, though, I want to point out is that the multiplicity of this denominator 0, which gives us this vertical asymptote at x equals 3, is 1. Okay? There's an implied 1 there, which means it's an odd multiplicity. So the multiplicity of the factors in the denominator tell us something special about those vertical asymptotes. When you have an odd multiplicity, the function will go to plus and minus infinity, but in opposite directions on either side. So on the left, we're diving down to negative infinity, and on the right-hand side of that vertical asymptote, we're growing up to positive. We're going up to positive infinity as x approaches 3 from both the left and right. Okay, so yeah, so an odd multiplicity dictates that they have to go in opposite directions from each other on either side of that vertical asymptote. An even multiplicity means that they will go either down to negative infinity together or up to positive infinity together. Okay, so that's a very useful little trick to use as well. Okay, So we still have the idea of the multiplicity of the numerator zeros telling us whether or not the graph crosses or touches the x-axis at that point. But now with these denominator zeros, zeros of the denominator polynomial, we find whether or not the graph will blow up in opposite directions or in the same direction on either side of that vertical asymptote. Okay, there we go. We've graphed that function. Next one. Oh, okay, here we go. We're given a rational function and we're supposed to figure out the correct graph. Select the graph of the rational function. Okay. Well, let's see. What is the x-intercept of this function? What is the 0 of the numerator? It occurs at x equals 4, right? This factor of -3/2 out front, it doesn't change intercepts at all. It doesn't change the zeros of the numerator, it doesn't change the zeros of the denominator. It's just because any number times 0 will be 0. So our graph must have an x-intercept at x equals 4. This one down here, this doesn't have an x-intercept. The graph does not touch the x-axis at x equals 4. So this graph is out. This cannot be correct. Similarly with this one, the graph does not touch or cross at x equals 4. Okay. Let's see. What other information can we glean? Well, it's in factored form, so we can get the zeros of the denominator very easily. And that will give us our vertical asymptotes. So we're going to have vertical asymptotes at x equals 2 and x equals -3. Okay. Oops. Okay, so x equals 2 and x equals -3. Does that help us? Well, both of the top graphs have vertical asymptotes at x equals 2 and x equals -3, so that didn't help us at all. What else can we get? What about the y-intercept? Well, the y-intercept will occur when we evaluate the function at 0. So what is f of 0? This is going to be -3 times -4 in the numerator, and in the denominator we're going to have 2 times -2 times 3, and what is this? This is going to be 12 over -12, so -1. So our y-intercept is at the point 0, -1. That's this point right here. Notice this is wrong. This is at +1, so this cannot be the graph. So this is the correct graph right there. Okay. Let's do another exercise here. Okay. Here we want to match each graph with its equation. Okay, I'm going to shrink this up a little bit and we'll see if we can get it all on one page here. Okay. So we have 4 graphs and 4 rational functions. We need to match them up. Well, let's see here. Maybe we could begin by graphing some intercepts. It looks to me like this bottom right function has a horizontal intercept at y equals maybe 1. Let me just move this up, zoom in just a little bit, and come on. Okay. Okay, so something like this, right? And what about this function over here? This one looks to me like it has a horizontal asymptote at y equals 0. What about this one up here? Okay, this one looks to me like it has a horizontal asymptote at y equals 1. Okay, so what about vertical asymptotes, though? While we're at it, while I've got the ruler out, let's draw those in. So this one looks to me like it's probably got a vertical asymptote about y equals 1. And this one also looks like it has a vertical asymptote at y equals 1. Close enough. And this one also, okay. Looks like it has, but notice they both dive down together. That's important information. Okay, it looks like they all have a vertical asymptote at x equals 1, don't they? Okay, so I've drawn the vertical and horizontal asymptotes. And notice this one on the top left corner here, this one does not have a horizontal asymptote. So this would have to be the top-heavy case, where the degree of the numerator is greater than the degree of the denominator. Can we find a polynomial where that's true? Which one of these is top-heavy? Well, this one is top-heavy. The numerator is degree 2, the denominator is degree 1. B, they're equal. C, they're equal. D is bottom-heavy. So this first one has to be A. Okay. Let's see, what about this one? Here we see that we have a 0 at x equals 2, but this is a 0 of multiplicity 2, or even multiplicity, right? And so we have a 0 of x equals, so we'll have a factor of x minus 2, but raised to the 2 power in the numerator. And then we have, what will we have in the denominator? Well, we'll have a factor of x minus 1, but it has to have an even power, because on either side of that vertical asymptote, the function is going up to positive infinity on both sides. So that means even degree of that 0. So let's see. So this function right here, notice, gives us a 0 where we touch the x-axis at x equals 2, and not cross, but just touch. And then this one gives us a vertical asymptote of 1, but the multiplicity is even. So I think this one is C. So we've used A and C. So this is choice C there. Okay. Let's look at this one here. Let's see. Okay, now we have a 0 at x equals 2, but it has to be of odd multiplicity. So we're gonna have a factor of x minus 2 in the numerator, but raised to an odd power. Oh, well, that's both B and D, so that doesn't help us. What else can we look at? Okay, well, notice that the functions both dive down to negative infinity on either side of that vertical asymptote, which means the multiplicity of the vertical asymptote will be even. Okay, so let's see. This one has odd multiplicity, but this one is even. So it has to be this one here. Okay, so it's going to be D. Let me get rid of that. So this will be choice D. And then, of course, this has to be choice B. Let's just verify. We do have a 0 at 2 and a y-intercept at 2. Let's see, do we get that from this function? Yeah, 2 will make the numerator 0, which gives us our 0 at x equals 2. And when I evaluate the function at x equals 0, I get -2 over -1, which is +2. And the degree of the multiplicity of the factor in the denominator is odd. And so I've got this behavior where the function is going in opposite directions on either side of that vertical asymptote, as we would expect. So yep, this has to be B. All right. So there we go. A fun little matching exercise. Okay. Here we have a kind of a business scenario. I'd never heard of a salt lamp before, but apparently you can take a salt crystal and like hollow it out and put a bulb in it, and I don't know, it looks pretty and some people like it, I guess. So manufacturing salt lamps has a fixed cost of $4,000 and a variable cost of $20 per item. Write the total cost function. So we want C of x, say. Let's use x to represent the number of lamps or items we produce. So remember that cost is given to us as the fixed cost plus the variable costs. The fixed cost is 4,000. The variable cost is $20 per item, so we got to multiply that by the number of items we produce. $20 times x, and there's our total cost function. Fixed cost and the variable costs. Write the average cost function. Okay, this is a new thing, and it's going to lead to a rational function. So the average cost function is denoted this way. We just it's C bar. We put a bar over the C to denote average. This is pretty standard notation. Okay, and what is this defined to be? We're going to define this to be, you take the total cost function and just divide it by x. Very simple. In other words, you take the cost of producing x items divided by the number of items you produce, and you get the average cost. So in our case, this will be 4,000 plus 20x divided by x. There we go. What is the average cost per lamp when producing 120 salt lamps? So we just want to compute C bar, the average cost of 120. Okay, so this will be 4,000 plus 20 times 120 divided by 120. Okay, I think I'll use the calculator for that. So we have 4,000. Oh, I'm going to need parentheses. 4,000 plus 20 times 120, close parentheses, divided by 120. Is that right? Yeah. So we get about $53, 33 repeating cents. Okay. So notice that the average cost incorporates the variable costs and fixed costs together. So if we just produce 120 lamps, on average, the cost per lamp is $53.33. Next, what does the average cost per lamp approach as more and more lamps are produced? Okay, so I'm going to use that notation I introduced at the very beginning. So the question is I'm going to kind of use the mathematical notation now. So as x goes to infinity, as we start producing tons and tons of these lamps, what does the average cost of x approach? Okay. So we use these arrows to you can read them as either goes to or approaches. So you would read this as x approaches infinity. The average cost approaches what? Okay. Well, I'm going to show you a little trick. Our average cost function, I'm just going to rewrite it. Okay? And I'm going to rewrite it in a form that's going to allow me to make sense of this idea of x going to infinity. So let's see, what was our average cost function? It was this, back up here, it was this 4,000, you know what, I can just do this. There we go. Make a copy of that. Oh, never mind. Yeah, it's okay. 4,000 plus 20x divided by x. Okay, so there's my average cost function. What I'm going to do is I'm going to change it. I'm going to keep it equivalent, but I'm going to change the look of it I'm going to multiply this by a very special form of 1. The highest degree power of x that occurs in this function is just the first power. So I'm going to multiply this by 1 over x over 1 over x. So as long as x is not 0, this is fine. And it's just 1. Okay? But what do I get then? So I'm going to get an equivalent expression. What am I going to get? I'm going to get 4,000 over x plus 20 over, well, x times 1 over x is just 1. Okay. So the point is that this expression is equivalent to this expression because I just multiplied this expression by 1. Okay? But now, look at this. Now, as x goes to infinity, this term, 4,000 over x, this is going to get closer and closer to 0 as x gets huge. Think of taking 4,000, dividing it by a million, a billion, a trillion, quadrillion, etc. Okay? As x gets bigger and bigger and bigger, that amount gets smaller and smaller and totally insignificant. It can get as close to 0 as you want to make it. Okay? And so the point is that as x goes to infinity, the average cost of each lamp will go to 20 over 1, which is 20. Okay? So this actually makes common sense, right? So if you produce tons and tons and tons of these salt lamps, your average cost is just going to approach your variable cost. Remember, this was the variable cost and this was the fixed. Okay, so as we make millions and millions of these salt lamps, the fixed cost will matter less and less and less. Okay, and it's going to get closer and closer to just the variable cost per lamp. So 20. Okay, so I want to point out this right here is a very useful trick with rational functions, okay? I'll use it again in the next one. All right. Okay, let's expand this. So, next exercise. Suppose the monthly sales volume, Y, in thousands of dollars of a product is related to monthly advertising expenditures, X, in thousands of dollars, according to the model Y equals 60X over X plus 6. Okay, so we have to keep in mind that both the sales volume is in thousands of dollars and the monthly advertising budget or expenditure which is denoted by X, is also in thousands of dollars. Okay, part A. What monthly sales will result if $2,100 is spent monthly on advertising? So that would be an X value of not 2,100. So if, notice, $2,100, if that's our advertising per month, since we're measuring the advertising expenditures in thousands of dollars, this would correspond with X equals, we just divide by 1,000 and we get 2.1. Okay? So think of it like this. This is my quantity in dollars, and you could think of it, it's kind of weird to think of it that way. Never mind. It's just X has to be 2.1 if we're measuring in thousands. Okay, so what we want to do is evaluate this function at X equals 2.1. So we get Y is going to equal 60 times 2.1 divided by 2.1 plus 6, which I'll use the calculator again. So we're going to have 60 times 2.1 divided by 2.1 plus 6, 8.1, right? Whatever. Okay, so we get 15.5 repeating, and this will be the monthly sales. So if we spend $2,100 monthly on advertising, we expect to make 15.5 repeating thousands of dollars in sales. So I multiply this by 1,000, and we're going to get $15,555.55 in monthly sales. Okay. B, what value makes the denominator 0? Well, that's pretty easy. X equals -6. Okay, but spending -$6,000 on advertising doesn't even make sense. So what is the implied domain of this model? Well, we can't spend negative money, right, on advertising. I suppose you could spend $0 on advertising. So I think the implied domain would be from 0 inclusive to positive infinity, right? Because it doesn't make sense to talk about negative spends on advertising. Okay, part D. What will be the maximum monthly sales volume as predicted by this model as more and more money is spent on advertising? Okay. Well, I'm going to use that trick again. Our model is this. Y is equal to 60x over x plus 6. Okay? In order to figure out our maximum monthly sales volume as predicted by this model, as notice this is the key phrase, as more and more money is spent on advertising. That's like saying as x goes to positive infinity, right? As more and more money is spent on advertising is the idea, same idea as our advertising budget goes is infinite. Okay, so what we want to do is, this is an idea that will come up in calculus if you take calculus. It's this idea of a limiting quantity to a function. How do we get that? Well, we do the trick that we did before. What I'm going to do is I'm going to rewrite this expression by multiplying the expression for the function by this special form of 1 over x over 1 over x. And I get 60 in the numerator divided by 1 plus 6 over x. Okay, so this expression is exactly equivalent to our previous expression, but it has the added benefit that now I can think of, well, what's going to happen to this function as x goes to infinity? Well, notice that x is only occurs in one place in this expression, right here in the 6 over x term in the denominator. So as x goes to infinity, that 6 over x will become more and more minuscule, and we say it will approach, we say that this term goes to 0. It limits to 0 as x goes to infinity. And thus, this expression will just equal 60 over 1 for very, very large values of x. It'll essentially be very, very close to just 60 over 1, which is 60. Okay? So what this is predicting is that as our advertising budget gets huge, gets bigger and bigger and bigger, our monthly sales volume should get closer and closer and closer to $60,000 because we're measuring in thousands of dollars. So you could write this out. You could say as x goes to infinity, y approaches 60. Okay? Another way to look at this is to graph the function. So I've done that already. Let me clear this out actually. So I've got 60x over x plus 6 there, and then I've got just a constant function at 60. And let's graph. I already put in Windows settings. Let's graph this. Okay. So yeah, so you see the function here. Let me pull this out so you can see this better. That red line is the line y equals 60. Okay, and this graph goes from, I think the units on the x-axis are every 5, so that would be negative 20 to, I think, to positive 100. And the y-axis is from 0 to 60 in units of 5 again. Okay, so now, so we see, yeah, the graph does get closer and closer to 60 as x gets larger and larger and larger, okay? Because 60 is a horizontal asymptote for this function, right? Right? If I take the, if I just go back to the original function and take the ratio, they're both degree 1 polynomials in the numerator and denominator. So I take the ratio of the leading coefficients, 60 and 1, and I get 60 for my horizontal asymptote. Okay, so yeah, that makes sense. And so we've answered the question. We're done. But there's kind of a natural question to ask here if you're thinking about this in a business context, and that is, well, how much should I spend on advertising, right? I mean, clearly, if I trace this function, you can see here, like at this point on the curve, let's see. So when I spend $17,273 approximately, I would expect $44,531 in sales for that month. Okay, well that's good. I'm getting more in sales than I'm spending on advertising. But notice, as I spend more and more and more on advertising, my sales do go up, but I'm getting to this point of diminishing returns, right? I'm putting in, more and more and more into advertising, but I'm getting, less bang for my buck. So the question is, a natural question to ask would be, well, I want to optimize this, right? Where do I get the most bang for my buck? Okay? Because really what's the problem here is that I want to, it's not just sales that I want to maximize, it's the sales minus the advertising costs that I want to maximize, right? So what would be the sales minus the advertising costs on a monthly basis? Well, that would be just the previous function, this 60x over x plus 6, minus the advertising budget, which is x. So let's put that in. 60x divided by, in parentheses, x plus 6. But now if I take off the advertising budget, I just minus x. There we go. So this is going to be sales minus our advertising costs. Okay, so now let's plot all three functions. Oh, and look at that. That black function. So the blue function is sales revenue in thousands of dollars per month. The black function is sales revenue minus advertising costs. And notice it has a maximum point there. If we trace, there we go. I can find out what that maximum point is, or approximately. In business, an approximate answer should be good enough, really. It looks to me like if I spend about $12,727 on advertising, my sales minus my costs, so I'm going to have $28,000 in profit, 28,000 plus dollars in profit. Okay. Notice if I keep spending more on advertising, what happens? My profits go down. Okay, because I'm getting to that point of diminishing returns until I get to the point where if I spend almost $53,000 per month in advertising, I'm not gonna make any money. Okay, so there we go. Okay, so hopefully this has been good to convince you that rational functions do have a place in a business setting. Okay, let's see here. All right, and I believe we answered all the questions. Yeah, so this concludes section 4.3 on rational functions.